Hello, Jackie.
Hello, Mr. Verdon.
Hello. Okay, so for today, we're going to discuss about the exercises for simple harmonic motion. So here, I prepared already a PDF file and I attached it into OneNote. So the question is about simple harmonic motion and the superposition of waves. So for example, we have this diagram, which is an object mass is placed on a frictionless surface and attached to a light horizontal spring. The other end of the spring is fixed. So this one is in the positive direction. The equilibrium position is at B. The direction B to C is taken to be positive. The object is released from position A. Again, this is released at position A. Normally, we release it at position C, but at this particular moment, this is released at position A.
Yeah.
And I execute simple harmonic motion between positions A and C. Right now, I want, what do you mean by simple harmonic motion? How would you define simple harmonic motion?
Simple harmonic motion is a special type of periodic motion or oscillation where the restoring force is directly proportional to the displacement and acts in the direction opposite to the displacement.
Very good. So restoring force is directly proportional to what?
To the displacement.
Directly proportional to the displacement.
And act in the opposite direction of displacement.
That's what I'm looking for. That and act at the opposite direction
to the displacement.
And act at the opposite direction to the displacement.
Yeah.
I'm going to ask you, where is the equilibrium position? Is it at A, B, or C?
It is at B.
It is at B. Do you think that if it's at the middle, it is automatically the equilibrium position? Do you think that in this particular case, it's the middle? Do you think that this is already the equilibrium position?
Like the question said, the equilibrium position is at B.
Very good. So the equilibrium position here is at B. So the restoring force is directly related to or proportional to the displacement and act at the opposite direction to the displacement, which is the equilibrium position. Now, we know that force is also equal to what?
MA.
Very good. So the net force is also equal to MA, mass times acceleration. That means that if the force is positive, then that means that the acceleration is also positive. So restoring force and what?
And acceleration.
Okay. Are directly proportional to the displacement. To the displacement from the what?
From the equilibrium.
Very good. From the equilibrium position.
Yeah.
Okay. And act at the opposite direction of to the displacement. Very good. So, what is the formula for Hooke's law?
It is F equals to K delta X.
Okay,
yeah.
Correct. So, F is equal to Kx.
Yeah.
F is equal to negative Kx.
Kx, yeah.
Right?
Yeah.
So, if that is the case, then that means that if the mass is here, then that means where is the restoring force? Yes, if the mass is here at the right side,
yeah.
Where is the restoring force?
It is at the left.
Very good, because that means that the restoring force follows the what? Follows the equilibrium position.
Yeah.
The equilibrium position is at the left of this mass, then that means that the restoring force is at the left. If the restoring force is negative, then that means that which one is the other negative?
The displacement. The
acceleration.
Yeah.
Right?
Yeah.
Acceleration, okay? So that means that if the force is a negative, then acceleration is also negative, right?
Right.
So that means that if the mass is here, that means that this is at the negative displacement, am I right?
Yeah.
So that means that the restoring force is where?
At the right.
Very good. So if the restoring force is positive, which one is also positive?
The acceleration is
very
also
good.
positive.
The acceleration is also positive. So we can just have a quick formula here. F is equal to ma, and this is also equal to negative kx, and that means that we can therefore conclude that acceleration is equal to what?
Negative k over n x.
Negative k over m times x. And what is k?
K is a constant.
Very good. This is the spring constant in this spring scale system, right?
Yeah.
Okay. And the spring's constant here is not changing, so it's constant, right?
Right.
And the mass is also not changing during the process. So which one are changing? The acceleration and the displacement. Very good. All right, let's proceed now. On the axis below, sketch a graph to show how the acceleration of the mass varies with the displacement from the equilibrium position B. So, if the displacement is at the negative side, here, it is the negative side, I'm going to ask you, if it's here, negative side, where is the acceleration? Is it at the positive or is it at the negative?
It is at the positive.
Very good. This is at the positive. Why again? That means that if this is at the negative side, then that means that the restoring force is where? To the
right.
Very good. If the restoring force is at the right, then that means that the acceleration is also to the right. Right?
Yeah.
Okay. How about here at 0?
The acceleration is 0 too.
Very good. Because why do you think that it is 0?
Because it is at the equilibrium position B.
It is at the equilibrium position. And to follow that, we know that F is equal to kx, right? So that means that x is equal to 0. That means that 0 displacement from the equilibrium position means 0 restoring force and 0 what? Acceleration.
Acceleration.
Okay, so this is gonna be A and this is gonna be B. And how about for C? If this is at positive displacement, where is the restoring force?
It is at the left.
Very good. So this corresponds to
negative acceleration.
Okay, so here we have the graph here, which is corresponding to ABC. Am I clear?
Yeah.
Okay, so in the previous lessons, we have already discussed about the position time graph and the velocity time graph. So right now, we are going to have the velocity time graph, but we need to consider that it was released from A. Okay, again, this was released from A. Okay, so if it's released from A, what is the velocity here? What is the velocity?
Velocity is 0.
Very good. Velocity is 0. Next. So that means that this is A. How about for B? What is the velocity? Is it still 0?
At where? A? B?
No, at B.
At B. At B, the velocity is maximum.
Very good. Is it positive or negative?
It is positive.
Very good, because it's moving to the right, okay?
Yeah.
So we have positive here. This is B. How about for C?
At C, the velocity is 0 too.
The velocity is 0. Why? Because here, this is at the maximum displacement here.
Yeah.
Are we clear? So how about for, what's the next one?
It will move to the B.
It will move to the B, which is at negative.
Yeah.
And this one is
0.
which is A.
Yeah.
Okay, so
Okay.
this will follow what? A sine graph or a cosine graph?
It is a sine graph.
Okay, there you go. Good job. Okay, next, you will proceed. Now, the question is about simple harmonic motion. We're given the period of oscillation. The distance of from A to B is a 0.040. This one is having acceleration time graph. Now, what do we mean by 0.040? For example, this one is 0.040 from A to B. What is this? What do we call this?
It is amplitude.
Very good. The amplitude, how do we define the amplitude? This is the maximum displacement from the what?
From the equilibrium position.
Very good. Maximum displacement from the equilibrium position. Right now, I'm going to ask you about what are the main characteristics of simple harmonic motion.
The first one is the acceleration is directly proportional to the negative displacement.
The acceleration is directly proportional to the
negative displacement.
Correct. And what else?
The second one is in the simple harmonic motion. It has one equilibrium position.
Correct. It has a constant. Okay. The acceleration is directly proportional to the negative of displacement.
Yeah.
And the other one is
in the simple harmonic motion, it has one equilibrium position.
It has one equilibrium position. And what's the other one?
The other one is period is independent of amplitude.
Very good. The period is independent of the amplitude. What else? The last one.
The last one.
Yes, the amplitude
is
and the what? The period are what? Are constant.
Constant. Yeah.
Are we clear? Because what does that mean if it's not constant? If the amplitude is not constant, that means, like, for example, I'm going to draw. So it's like this, right? And it started here and here and here. What do you mean if it's not constant? What does that mean?
It means we have friction.
Very good. That means that this is not moving in a frictionless surface. That means that we call this damping. Okay, damping is a word that HL students are using for topic 9, but we don't need to discuss that. So, but then again, this is the decreasing of the amplitude because there's friction or there are other forces acting on the system. Are we clear?
Yeah.
Okay, so X has a mass of 0.28 kilograms. Calculate the maximum force acting on X. So how do we calculate this?
We need to use the formula F equals to ma.
F is equal to ma. Very good. We have the mass, but we don't have acceleration. We have the we have the amplitude and we have the period. So how do we get the acceleration?
We can get the acceleration from the graph because it provided us with the graph.
Very good. So the graph has the maximum acceleration, which is what? Equal to what?
2.6.
2.6. So that means that we can have 0.28 times what?
Times 2.6.
0.28 times 2.6. The answer is
0.728.
very good. 0.728. And what is the unit here?
Newton.
Very good. The unit here is Newton. That's it, right? Did you understand the problems?
Yeah.
All right, that's great. You did a very good job, and see you next time.
Okay. Bye.
Bye.